Well, thank you very much for the invitation. Um, I'm very excited to tell you about something I worked on earlier this year. And the topic is diameter of Cayley graphs, basically. So I'll get into my long-winded title um, uh, in due course. So before I begin, let me just say that everything is joint work with Urban Jezernik, who's at the Renyi Institute in Budapest. So, okay, so what's a Cayley graph? Um, so Cayley graph, you probably all know. You take any group, so a finite group, and you take some set of generators, um, any set of generators, and you form a Cayley graph by um, taking a vertex for each element of your group and joining two vertices whenever they differ by one of your generators. So this is a graph that captures the manner in which your generators generate your group, essentially. And what's the diameter of a graph? Well, for any two vertices in your graph, there's a notion of graph distance, which is the length of the shortest path which joins them in the graph. And the diameter is the worst that can ever be. So it's the longest, shortest path. So you take the worst two vertices in your graph and you ask how far apart they are in the graph. So here's a simple example. I've made the Cayley graph of Z mod 12, and just for variety, I've taken the generating set that you might not first think of, just to illustrate that, okay, it doesn't have to be the standard generating set. It can be any generating set. And the Cayley graph in this instance looks like this, this funny looking wheel. And you can just inspect, see that the diameter is 3. So the two opposite vertices, shortest path that joins them has length 3. Okay, so here's a basic lemma, which just says that if you have a Cayley graph, well, Cayley graphs are, they're totally symmetric. So I can, if I'm asking for the worst distance, I may as well fix one of them to be the identity. And then the diameter is just the smallest integer k, such that any element in my group can be written as a word of length at most k in my generators. So this is an easier way of thinking about diameter in the case of Cayley graphs. It's just how long does it take my generators to cover my group. Okay, so let's look at a couple of examples just to orient ourselves. So here's the most basic example. You just take the cyclic group of order n, and you take a generator as your set of generators. And it looks like this cycle, and the diameter is clearly n over 2. And the point of this is just to illustrate that the diameter can be very large. So the size of the group here is n, and the diameter is n over 2, which is really enormous. And this is actually a general symptom of abelianness. So here's an easy lemma. If you have an abelian group and you have a generating set of size s, then the diameter of your Cayley graph with respect to this generating set of size s is at least some constant times the size of your group to the power 1 over s. So it's at least a power of the size of the group. And it's easy to see why this is true, is because you have a generating set, and as you're taking powers of your generating set, you can't actually generate too many different elements just because all your generators commute. So you're not getting as many different elements as you might hope for. So abelian groups have large diameter. Let's look at another example. So here's a group formed as a particular semi-direct product involving some alternating groups and some cyclic groups. I wonder if anybody recognizes this group, any chance? And by the way, please, if you have any questions at any point, please interrupt me. I like being interrupted. So does anybody recognize this group?
Does it depend on the action?
Yeah, I haven't told you what the action is.
I'm just trying to stall to think more.
Okay. It was intensively studied in the 80s, this group. Okay, so maybe sorry? Maybe a picture will help. So here's a picture. So this is actually the group of all permutations that you can all permutations of the facets of a Rubik's cube that you obtain through the standard operations on a Rubik's cube. So I can take this is an enormous group. It has order like 10 to the 20, something like that. And it's got a generating set of size about 20, corresponding to just twisting the faces, right? And what's the Cayley graph of this group? So it's an enormous graph where you have a vertex for each possible configuration of the Rubik's cube, and two configurations are joined whenever you get from one to the other by turning one of the faces. And what's the diameter? So the diameter it's the worst distance to the identity. So you take the worst possible configuration and you ask, how far is this from the identity in the graph? Which is just a way of saying, how long does it take to solve the Rubik's cube in the worst possible case? Okay, so this is quite a natural. This illustrates this quite a natural concept for somehow naturally arising groups.
And what is the answer?
So the answer, good question. The answer turns out to be 20, and this is only established in 2010. So it's a big computational project completed by these authors, Rokiki, Kosiemba, Davidson, and Dethridge. And they have a website about it called cube20.org, where you can look at a bunch of data. So in particular, they did a bit more than establishing that the diameter is 20. They also tabulated the number of different positions you can obtain in so many steps from the identity. And I've plotted them here. So the x-axis is number of steps, and the y-axis is number of different positions. So it's how quickly the generators are growing. And let me emphasize that this is a logarithmic scale on the y-axis. So this is basically perfect exponential growth until the very end of the growth, in which case you just sort of run out of space. And then in the last couple of steps, they fill up the rest of the group. So this is a nice example because the exponential growth is so clear, but this just illustrates that this is more the typical behavior you expect for a somehow typical Cayley graph. You really expect your generators to really blow up until the end. And yes, let me also emphasize that the size of this group is enormous. It's about 10 to the 20, and the diameter is only 20. So the diameter is really much smaller than the size of the group. It's basically logarithmic. Okay, so let's look at another example. Let's look at the symmetric group, which is sort of the group of all permutations of n objects. And the generating set, I'm going to take all transpositions of neighboring elements. So the transposition 6, 7 is in my generating set, but the transposition 6, 10 is not. And you ask, what's the diameter of the symmetric group with respect to this generating set? And this is equivalent to what computer scientists would call bubble sort. So you have, in other words, if you want to think of this in terms of solving something like in the Rubik's Cube case, you start with an unsorted list, and you want to sort this list in as few steps as possible by swapping neighboring elements, which is exactly the bubble sort algorithm. And it's a standard fact, exercise, theorem, something, that the worst case is when the list is in exactly the wrong order, when it's anti-sorted. And in this case, it takes precisely n choose 2 swaps to get it back to the right order. So the Cayley graph in this case is n choose 2. So again, this is a case where the size of the group is enormous. It's n factorial, but the diameter is comparatively small. It's about n squared.
And typically, it's much smaller than n over 2?
Yes. Yeah, I'll get to that in a moment. And I think there's no case known in which it's worse than about n squared. So this, well, I'll get to all this in a moment. Let me just describe what I've drawn here. So this is the case n equals 4, this Cayley graph. And actually, in this case, is a truncated octahedron, just for curiosity's sake. Okay, yeah, so let's talk about the symmetric group a little bit more. Yeah, so it's basically, it's not expected that it should ever be worse than about n squared. And so let me talk about why this might be true. So in the case where your generating set contains a transposition, it's actually not at all hard to prove that the diameter must be at least no worse than n cubed, say. And the reason for that is pretty easy to see. So I've drawn a graph here in the case n equals 6, in which have a generating set, which in particular includes this transposition 1, 2. And what I can do is I can act on that transposition by conjugation. I can conjugate it by my other generators, and that will give me more transpositions. So in this case, I had a transposition and I had a couple of other random generators. And in the first step of conjugating my transposition by my other random generators, I obtained these purple transpositions. And then the second step, I obtained these green transpositions. And the third step, I obtained this last light blue transposition. My point about this is just that you must obtain all transpositions pretty quickly. In fact, there are only n squared transpositions. So it only takes you, at worst, n squared steps to get all transpositions. And once you have all transpositions, then any permutation is a product of n transpositions. So the diameter is at worst n cubed. And even this is pessimistic. So if you actually have a transposition and 2 random generators, then what you can prove is that this idea that you get all transposition in n squared steps is actually very pessimistic, because there are n squared transpositions in total, and this looks like a random graph, so really it should have logarithmic diameter. So what you can show is that you get all transpositions in log n steps, and then once you have all transpositions, again, it's only n steps to get the entire group. So
with high probability?
Yes, with high probability. So actually, I'll say that several times in this talk. I'll say something is true in the random case. And obviously what I mean is with probability tending to 1 as whatever parameters are relevant tend to infinity. So yeah, so in the case where you have 2 random generators and a transposition, with high probability, the diameter is bounded by n log n. Okay, so so the case of the symmetric group is very well studied. And in all cases, the diameter seems to be bounded by n squared, really. Certainly no worse than polynomial in n, and that's been a conjecture for a long time. That's not quite known. And this inspired Babai to speculate that maybe this is true. Maybe this phenomenon is true for any non-abelian finite simple group. So this is what Babai conjectured. Babai said if you take any non-abelian finite simple group and you take any generating set, then the diameter of the Cayley graph is no worse than polylogarithmic in the size of the group. So to illustrate, in the case of the symmetric group, the size of the group is n factorial. So log n factorial is about n log n. So this is saying that the diameter should be bounded by a polynomial in n.
And the O1 is absolute, right? The constant is absolute for all simple groups.
That's right. Yeah. You know, this is motivated by the symmetric group. So maybe the big O1 is 2. Who knows? You know, It's certainly at least 2, as the example of bubble sort shows. Okay, if there are any questions, please interrupt me. Otherwise, I'll barrel on.
I'm a bit puzzled. You jumped from, I mean, you started with a billion and now we reached non-billion, and we didn't talk too much about solvable groups. Is it like a billion or like non-billion or like simple? Where is it on the spectrum?
That's a good question.
Complicated solvable groups.
Yeah, I think I don't know exactly. I don't know what the conjecture should be, but I would say somehow typically a non-degenerate solvable group should behave more like the simple case.
More like the simple case.
Yeah, but you have to be very careful about what you're conjecturing exactly.
Yeah, what is non-degenerate? Because probably nilpotent, for nilpotent or for P group.
For nilpotent, it should be more like the abelian case. There should be some polynomial bound, and if you have like the Heisenberg group and you have some generators, then those generators can grow at worst a polynomial rate.
Okay.
But as soon as you're past that, once you're in the solvable case, then you should be growing exponentially. But Babai's conjecture is very much an idealized form, which is at least for in the non-abelian simple case. At least in that case, we should have an exponential blow up.
Thanks.
Okay, so I want to tell you the state of our knowledge about Babai's conjecture. And to do that, I have to tell you what all finite simple groups are, which is not easy. But here's a dumb diagram that I've made that will be good enough for this talk. So in this talk, it will not offend me if you consider all finite simple groups to be SLNQ for some values of n and q. So here is my dumb graph of all finite simple groups. So SLNQ is the group of all matrices acting on FQ to the n, where q is some prime power of unit determinant. So if n is small, like 2 or 3, you have like SL2Q and SL3Q, which are down here. And if Q is small and n is large, then you have something like SLN2, which is up here in this high rank area. And you can also whimsically consider SLN1, sort of SLN over the field with one element to be the symmetric group. Okay. And then in the worst case, both n and q are large and they're up in this high rank territory. So this picture is very wrong in any number of ways. So here, I'll list all the ways. First of all, we're missing all the exceptional simple groups, but I don't really care because we're doing asymptotic group theory. So they're only finite, no, not exceptional. All sporadic simple groups are not listed. So we're doing asymptotic group theory. So there are only finitely many sporadic groups, so I don't care. Another thing you might complain about is that SLNQ is not simple, which is true, but that's really not important. But okay, let me make this graph a little bit more honest. So here I've replaced SLNQ in bounded rank with some arbitrary group of Lie type. And we're not going to worry too much about those, so you don't have to think about those. But in high rank, mercifully, really there are only 4 types, which are the special linear group, the symplectic group, the orthogonal group, and the special unitary group. And really, when I say the orthogonal group, I have to take the derived subgroup of the orthogonal group. And in each of these cases, I need to quotient by the center. Okay, so that's a more honest picture. But as I said, it will not hurt your understanding of this talk if you only think of SLNQ. Okay, so what is known about Babai's conjecture? So I'm going to break Babai's conjecture down into a bunch of different cases, depending on where we are in this diagram, depending on whether we're small rank or so on. And the other way I'm going to break it down is, well, Babai's conjecture is about what happens in the worst case. So what happens for an arbitrary generating set. But it's also very interesting in its own right, but also as a test case to ask what happens for a typical generating set. So I'm going to break it down in these two ways. And first of all, so in bounded rank, you have this arbitrary Lie type, whatever, but in bounded rank, we know a lot. So we certainly know that Babai's conjecture is true. And you can start asking even stronger things. So for instance, for a typical generating set, we know that the diameter is actually logarithmic. It's not polylogarithmic, it's logarithmic. Okay, so I'm not going to worry too much about bounded rank. In fact, I'm not going to talk about bounded rank at all. In unbounded rank, so the first case of unbounded rank, when you're on this left side of the diagram, is when you take q equals 1, is the case of the symmetric group. And we actually know quite a lot in the case of the symmetric group as well, as another sort of special case. So there's some work by Helfgott, Seress, and Zook, which shows that for typical generators of the symmetric group, the diameter is about n squared, which is what we actually expect it to be in the worst case, but they showed that this is true for typical generators. So certainly we know Babai's conjecture is true in that case. And in the case of arbitrary generators for the symmetric group, there was later work by Helfgott and Seress, which showed that the diameter, okay, maybe it's not, we don't know that it's necessarily polynomial, but we know it's quasi-polynomial, so exponential in a power of log. So I've made that sort of light green on this diagram in the sense that we sort of almost know Babai's conjecture is true in that case, but we don't quite know it's true. My main interest in this talk is the rest of the cases in large rank. So if you have a large rank and you have SLNQ, where Q is actually bigger than 1. So Q is like 2 or 5 or 9.
Sorry, Sean. I have a question. For random generators in a symmetric group of order n, how do they actually sample this set of generators?
Uniformly. So when I say random generators, I mean.
Okay. So it's not like uniformly. You take uniformly 10 generators.
Yeah, exactly.
Okay.
Exactly. That's what I mean by typical. Yeah.
Okay. Thanks.
So you fix usually 2, right? You fix just 2 elements or something.
That's right. That's right.
Yeah, sure.
Yeah, I'll talk about that specific argument in a little more detail, actually. Anyway, so for SLNQ, for Q a bit larger than 1, really we know very little. So the size of the group is something like Q to the n squared, Q to the constant times n squared. And what we know is that at least it's not worse than about Q to the n. But Babai's conjecture is essentially saying that it should be polynomial in n. So this is still sort of exponentially far from what we expect to be true. Okay, so what I want to talk about today is I want to talk about some modest progress on Babai's conjecture, where we're going to turn one of these red boxes green. So we're going to turn that red box green. We're in the situation where we're in high rank over a small field, and we have typical generators. So something like SLN2 with typical generators. And what we claim is that in this situation, indeed Babai's conjecture holds. And we have some caveats that I'll talk about. Okay, so just in reference to my previous diagram, where are we? So as I said, we're not worried about bounded rank. We're up in this territory of high rank over a small field. So like SLN2 is a good group to have in mind. Okay, so are there any? Well, let me state what we actually. Let me state a specific theorem. So I've just written down Babai's conjecture again here, which says that the diameter of any non-abelian finite simple group is bounded by polylogarithm. And so what did we prove? So we proved, in the case of, there's 2 parts to what we proved. So first of all, for SLNP, when P is actually prime and of bounded size, then as long as you have at least 3 generators, then Babai's conjecture, at least 3 random generators, then Babai's conjecture holds with high probability. And the other part of what we proved is, okay, so that part holds only for SLN and only when the size of the field is prime. So the other part of what we proved is if you have a general classical group and you have an arbitrary finite field, FQ, then still it's true as long as you have sufficiently many random generators depending only on Q. So I've written down Q to the 100, which might be the right number. Okay, any questions about that before I start waving my hands about the proof?
So in the first case, by bounded, you mean bounded with n? What is bounded?
Bounded okay, what is bounded? Bounded. So
you take n to infinity and p can be, I don't know, 11 or 1.
So I think specifically what I mean is that the diameter is bounded by something like n to the log p. So
okay, now I understand.
Yeah.
Bounded it with respect to the O of 1 that we have.
Exactly, yeah.
Thank you.
No problem.
So this is also why you say that in the second theorem, you're not in the diagonal, in the rightmost, in the right upper corner of the diagram.
So in the second part, I'm not making a specific hypothesis that Q should be bounded, but it's kind of only interesting if Q is bounded, because I want to, Babai's conjecture is really interesting if you have a bounded number of generators. Once the number of generators becomes very large, things become a bit more trivial. So actually, if Q has size about n, if Q has size comparable to about n, then this bound becomes trivial compared to there's a theorem of Allon and Roykman, I think, which says that whenever you have a Cayley graph and you have at least log g generators, then that has a logarithmic diameter. So once you have a large number of generators compared to the size of the group, then things become trivial. Okay, so all right, so I want to give you an idea of what you can do to prove something like this. So we're following, there's this program that we call Pyber's program, which is something like a way of breaking down. So Pyber's program says you should think of Babai's conjecture as consisting of 3 separate problems. I'm going to tell you what these are, but first I need to tell you what degree is. So it's easiest to understand in the case of the symmetric group. So if you have a permutation has some number of fixed points and has some number of points it moves. So the degree is the number of points it moves. And I might also call that the support. So these are sort of interchangeable words in the literature. So I want an analog of this for SLNQ. So for SLNQ, I say the degree is the rank of G minus the identity. So an element of small degree is an element which looks like the identity plus a small rank element. So for instance, an element of degree 1 is a transvection. So for instance, you might think of the coordinate transvections, which look like a matrix which has 1s on the diagonal and one other non-zero entry. So a transvection looks like you fix some hyperplane and some direction in the hyperplane, and you fix everything in the hyperplane and you move everything off the hyperplane in the direction of your direction. So in SLNQ, this is analogous to like a transposition in the symmetric group, or a 3-cycle maybe. Okay, so in SLNQ, there's a new wrinkle in what might happen, which is that, okay, I might have an element which it's not necessarily close to the identity in this sense, but it might be close to another scalar. So I would call this a support. So an element of small support looks like some scalar transformation plus plus a low rank matrix. Okay, so I need both concepts. So what is Pyber's program? It says, so we start with some generating set, and we want to get from this generating set to the whole group. So what Pyber's program says is, well, first you should worry about getting some element of degree which is a bit less than n. So step 1 says get from your generators to some element which has degree at most 0.99 times n. And step 2 says, okay, once you have some element of degree which is a bit less than n, then think about how you're going to get from that element to an element of minimal degree. So in the case of the symmetric group or the alternating group, that means getting to a 2 cycle or to a 3 cycle. In the case of SLNQ, it's worrying about how you're going to find a transvection. And then finally, there's step 3, which is once you have this element of minimal degree, then get from that to the rest of the group. So we saw this earlier in the case of the symmetric group. So if you have a generating set which contains a transposition, then it's actually not at all hard to prove that that you can quickly cover the rest of the group, just because you quickly obtain all other transpositions, and then once you have all transpositions, you quickly get the rest of the group. But let me caution that although that was trivial in the case of the symmetric group because there are only n squared transpositions, it's really not at all trivial for SLNQ. Because for SLNQ, the number of transpositions is about q to the 2n. So it's exponential in n. So this trivial argument does not work for SLNQ. Okay, so to illustrate this program, let me describe what Helfgott, Seress, and Zuk do for Cayley graphs of the symmetric group with respect to typical generators. And yeah, so this is slightly this and other arguments to do with the symmetric group are what motivate the description of Pyber's program. But so here's what this is how the Helfgott, Seress, Zuk argument goes. So you have, just to remind you, we have the symmetric group and we have 2 random generators, and we're trying to bound the diameter of the Cayley graph. So the first step, we're looking for some element of degree a bit less than n. So we're trying to find an element with lots of fixed points. And you do that by using the following trick. You first look at the following elements. You look at g times h squared, g times h cubed, up to g times h to the k for some slowly growing k. And what you note about these elements is they kind of look like independent elements, or they look at least sort of pairwise independent. And if you have a random permutation and you look at the longest cycle of a random permutation, that has size typically comparable to n. So it happens with positive probability that there should be a very long cycle. And now if you have these large number of kind of independent looking elements, then it becomes close to certain that one of these guys will have a long cycle. So once you have some g times h to the j, which has a long cycle, then you can look at g times h to the j to the power of the length of that cycle, and that will have degree much less than n. So that will have a huge number of fixed points. So that's step 1. So at that point, you have some element with degree less than n.
Sean, probably it's trivial just to make sure that I follow. So the probability that this element is a cycle of length L is 0, right? Because otherwise you will get a trivial element.
Yes, that's true.
Yeah,
you do have
but
to,
this is obviously going to 0, so it's not a problem.
Right,
just to make sure that I don't miss them. Yeah,
no, that's absolutely right. You do have to make sure that that element is non-trivial, is degree less than n and non-trivial. That point will remain true for the rest of this argument, I think. So step 2 consists of you have some element of you have an element of degree less than n over 10, and we're trying to reduce the size of the support now. And what you can do is you can conjugate that element by your generators. So you end up moving the support around a lot. And then you can take two of these elements and you can take the commutator of them. And as long as the supports, as long as they overlap, but not by too much, then the support will reduce a lot. So you do this argument repeatedly, and eventually what you get is an element of minimal support. So you get a 3 cycle in the end. Okay, so once you get a 3 cycle, then as I've described before, it's easy to show that only after another n steps or so you get everything. So so that's the description of the Helfgott-Schreier-Zug argument in the case of the symmetric group. Okay, so we'd like to do something like this in the case of SLNQ, so like SLN2, something like that, which suggests that the first thing we should do is we should look at the random walk generated by our generators, and we should try to find some element, which is not too long a word in our generators, that has degree much less than n.
So Sean, a quick question. I mean, these steps are not, let's say you reach an element in step 1, then you need to use it several times in the next steps. Shouldn't you take a power of the? So
you do use so for instance, in the second step, I've got this. You're right. I've got this word of length about n, which has degree much less than n. And in the second step, I'm conjugating that. So whenever I conjugate it, this is only additive, right? So I obtain other words which look like a conjugate of my original word. And then you're right, then I'm taking commutators. So at that point, it is sort of multiplicative. So my word does start growing quite a lot. But the good thing is that this process is actually pretty quick. So there are only about log n commutators that happen in this process. So I'm multiplying by 4, but not too many times.
Okay.
So my word doesn't grow too quickly.
Okay.
Yeah. And then the same thing in step 3. So at some point I get a 3 cycle, which is given by some word, and then I conjugate that around, but none of those words grow very much. So I end up writing all 3 cycles in a word, which is not too long.
Okay.
Yeah. Okay, so we'd like to do step 1 for SLNQ. But actually we don't. So we decide we're not going to do that. So we do the opposite of step 1. We actually prove that step 1 is just too hard. So so let W be any word in the free group, and I'm going to write W bar for W evaluated at my generators. Step 1 is saying I'd like to find some such word which has degree less than n. And what we prove is that actually that just doesn't happen. So if at least that doesn't happen before about step n. So if you take a word which has length much less than n, like length n over 10 or something like that, and you ask, does this word have support which is less than 0.99 times n, say, then the answer, this happens with exponentially small probability. So we were trying to find a word which has small support, and what actually we proved is that basically all words in the support of our random walk have nearly maximal support. So this is like the antithesis to step 1, is that the entire support of the random walk is maximal degree. Okay, so we're going to find a replacement for step 1. We're going to do something instead of finding an element of minimal degree, and it comes from the observation that this is actually a good thing in the following sense. So we know that all points in our random walk after about n over 10 steps are generic in the sense of having almost maximal support. And then there are quite strong character bounds available, which say that if you take an irreducible character and you evaluate it at an element which has nearly maximal support, then those character values are very, very small, which means that the random walk is something like equidistributed. Okay, and this is only with respect to normal subsets. So a normal subset is a subset which is invariant under conjugation, so like a union of conjugacy classes. Think of like Fourier analysis. So if you have a distribution and you know all its non-zero Fourier coefficients are very small, that means that the distribution is close to equidistributed. But because these are character bounds rather than actual Fourier coefficient bounds, we only have such a statement for normal subsets, but still the message is kind of the same. And the value of this is I can pick my favorite large normal subset. And my favorite large normal subset is the set of all elements which sort of get step 2 done immediately. So you take all elements G which have a smallish power which has minimal degree. So in the case of SLNQ, this is like looking for an element which has some two-dimensional subspace on which it acts as a transvection, and everywhere else it acts semi-simply and with eigenvalues which do not have too large a degree, so that I can kill all those eigenvalues by taking a smallish power. So there's some calculation to be done here that I'm not getting into, which says that this subset is large, but that's the idea. Okay, so I want to explain in a bit more detail how this actually works. So first of all, let me describe these character bounds. So in the past few years, there have been quite a few quite strong character bounds that have been proved, and so we're using this result that was proved by Gronick, Larson, and Tiet from earlier this year, and they have a result for all classical groups. And what it states is that if you have a classical group and you have an irreducible character of that classical group, and you evaluate that character on some element which has degree at least 1 minus delta times n, then the value of the character is bounded by the degree to the epsilon, where delta depends only on epsilon. And this combines really well with what I was just saying about the failure of step 1. So this corollary follows from this character bound and this failure of step 1 theorem. So if I take some character ratio, by which I mean the value of the character divided by the degree, and I evaluate this on some word of length less than a constant times n, length than n over 10, something like that, then what can happen? So either the support of the word is small, but we prove that that has exponentially small probability, so that's not important. And the other case is that the support is large, in which case the character bound says that the character value is very small. So we deduce that the expected value of this character ratio is exponentially small. Okay, so why is that good? So the next thing I need to explain is, right, so let me just remind you why that's good. So why that's good is because I have the support of my random walk, and I know all the character values are small, and so I expect that random walk to look equidistributed. I expect it to hit any large normal subset. I'm going to explain the argument that we have that shows that you do hit a large normal subset. And this is a generalization of that trick that appeared in the Helfgott, Seress, Zook argument, where you look at G times H squared, and so on. It's like a more powerful version of that trick. So I call it the x times w of y z trick. So you look at all words in 3 generators. So this is the point at which we need 3 generators. You look at all words of the specific form where you just take the letter x, and then you take an arbitrary word in y and z. And you look at all those words, and those should look sort of pairwise independent. And I'm going to apply the second moment method to this collection of words. So I'm just going to count all those words which land in my normal subset. So why is that going to be good for the second moment method? So the first moment, the expectation, this is trivial because each of these words has the form some function of y and z times x, and x is uniformly independent. So the first moment is easy to calculate. It's just the density of the set times the number of words I'm talking about. And the second moment is a short calculation that I won't get into, but it reduces quickly to these, you can reduce it quickly to these expected character values. So in the end, you have a result that says the probability that none of these words lands in my normal subset is bounded by 1 over the density times the worst character ratio. And I'm taking a large normal subset, so 1 over the density is not too large. And I've got these strong character bounds that say the expected character ratios are very small. So the outcome is that we know that there's some word of not too long a length which lands in our favorite normal subset. And yeah, so as I explained, that means that you can take a power of this element and you get to an element of minimal degree. So that's the end of how we essentially skip step 1 and go straight to step 2. Are there any questions about that? So the next thing I want to explain is what we do about step 3. So step 3, I remind you, is you have a generating set, and now you have a transvection. You have an element of minimal degree, and you want to get from that element to everything in the group. And as I cautioned, this is although this was trivial for the symmetric group, it's actually very non-trivial for SLNQ, and we actually don't have a fully satisfactory solution. But we have 2 options. Well, the first option is, well, when the classical group is SLN, so not the special unitary group, not any of those other ones, but it is SLN and the field is prime, then we actually do have a complete solution in this case. So this is a theorem that was proved by Zoltan Halasi earlier this year. It appeared on the archive not long before our paper, which says that Babai's conjecture is true in this case. So if you have a generating set of SLNP and it includes a transvection, then the diameter is at most polynomial in n. So this is great for us. So that just gets the job done. But the downside is it only works for SLNP. This is not known for other classical types yet, and there seem to be I expect something like this to be proved eventually for the other classical groups and for non-prime fields, but there are a lot of things in the way that make that challenging.
So this is a difficult work. I guess.
It's not difficult in the sense of long. It's something like a 15-page paper, but it's quite ingenious. It's actually a very beautiful argument. Anyway. Okay, so but we have another option. And the other option relates to what I was saying in the symmetric group. So in the symmetric group, once you have a transvection, you can say, okay, at worst, it's n squared steps to get all transvections. But actually, typically, for a random generating set, you expect that to happen much more quickly. So that's what we try to prove. So this is what we did. So you take your suppose you take your SLNQ and you act on, just say you just act on FQ to the n. So you look at this, the Schreier graph. Then you expect this to be an expander graph. If you don't know what that means, you can just think of it as a strong form of having logarithmic diameter. To give you a sense of why this is true, what is this in the symmetric group case? So if you take a random permutations and you act on 1 up to n, and you draw that Schreier graph, that is none other than a random graph. So random graphs are expander graphs. So you expect a similar thing to be true for SLNQ. The same thing with small powers of the natural module. So if you act on pairs of vectors or triples of vectors. And once you know that's true, then, well, once you have a transvection and you act on that transvection by conjugation, that permutation action is a component of one of these, component of, I think, the 4th power, maybe the 2nd power of the natural module. So if you know that the diameter of this graph is small, then you're done. So this is what we prove, but unfortunately, we don't know how to prove that for just 2 generators or just 3 generators. But we proved that it's true as long as you have at least q to the 10 generators, say, for the natural module, or a bit more for small powers of the natural module. Let me just mention that this is, in the case of the symmetric group, this is work of Friedman, Zhu, Roykman, Stern, and Tillich from 1998. Okay, so that I'll just close with a few open problems, and the first open problem is naturally, it's pretty natural in light of this last slide. So the question is just consider this Schreier graph. So you take SLN2 and you take 2 random generators and you act on F2 to the n. The conjecture is that this should be an expander graph. And so this is a graph with 2 to the n minus 1 vertices. And if you compute the spectrum, if you look at this and if you draw these things, they basically look just like random graphs. I don't know any reason that they shouldn't behave in exactly the same way as a random graph does. So I really expect this to be a random graph as soon as you have at least 2 generators.
So you expect it to have a nearly optimal spectral gap, right?
Yeah.
Not just expand.
Yes, I do. But we don't know how to prove that. We only know how to prove this as long as you have sufficiently many generators, like maybe 10 generators in this case. I'm not sure what it is exactly. So that's the first open question. The second one, it relates to this failure of step 1 idea. So you take a word of length not too long, so n over 10 or so, and we proved that that the support is nearly maximal. So in particular, the word is almost surely not trivial, because if you're trivial, then your degree is 0. So we really use the requirement that the length be less than n over 10 here. But we don't expect that to be necessary. So if you take a word which has length 10n, say, then it should still be true that the probability that the word is trivial is exponentially small. And we don't know how to prove that because all our methods, they're very much using linear algebra. So you're looking at the trajectory of a vector and you're thinking about what this looks like in this vector space. But once you have more than n steps, then we don't know what to do. So here's a particularly embarrassing analogous conjecture in the case of the symmetric group, which is that if you take a word of length barely more than square root n, can you show that the probability that this word is trivial is tending to 0? So that's a particularly embarrassing form because it's hard to believe that it should be otherwise, that it could be otherwise. Leo, are you trying to speak? Because I think you might be muted.
Yeah, I closed the mic by mistake.
Yeah.
Does it have an analog in number theory? So if you because it looks like this anatomy between integers and numbers.
Well, it's more complicated because I'm taking an arbitrary word. So I'm really looking at the way these permutations are multiplying.
Yeah, so it's something else. Because this L comes from the free group and not, I mean, the length of the word.
Yeah.
Not so it's something from outside.
Yes. Yeah.
So there is no free group in the number theory analogy. There's no free object. No. Okay.
Yeah.
So yeah, I understand.
Okay, let me close with one more open problem, which I think is an interesting one. So there's a very famous conjecture which says that if you take the alternating group and you take 2 random generators, well, okay, let me not call it a conjecture, but a question. So the question is, if you have the alternating group and you have 2 random generators, the question is that graph an expander graph? If you take that Cayley graph, does it have logarithmic diameter? Is it an expander graph? And I'm calling it a question because I'm not sure anybody's been brave enough to conjecture it. There's not a clear consensus on whether it's true. But my question is, suppose I also give you a transposition for free. Oh, okay, this slide's a bit dumb because a transposition is not in the alternating group. But you know what I mean. Take a 3 cycle or change AN to be the symmetric group. So suppose I give you a 2 cycle or a 3 cycle for free and you have 2 random generators. The question is this graph an expander graph? And the interesting thing in this case is that it's very easy to show that the diameter is optimal. The diameter is n log n. And that's just because if you have one 3 cycle to begin with, then you have all other 3 cycles in log n steps, and then you have n log n steps, you cover the group. But I don't think it's known, and it doesn't. It's not known, and it's not trivial that this should have a spectral gap. So this should be an expander graph. Okay, so I'll stop there. Thank you very much for listening.
Thank you very much for this very interesting talk. Questions? Are there any more questions?
Yeah, I have another question. So if you know the first conjecture you raised, can you plug it in your work and then you get?
Yeah. So this, if we knew this, well, not for the natural module, but for f2 to the n squared. So the action on pairs of vectors. Then yeah, we could plug it into our work and we could get the same thing for 3 random generators instead of q to the 10 or whatever. Yeah.
Okay.
Gil, you wanted to ask something?
No, I just clapped.
And another question. So you had this XW trick.
Yeah.
Okay. So you can use it for the symmetric group and get something better?
Yes, with the caveat that you need 3 random generators. So we wrote this in our paper too as an appendix. So so this relates to, so in the Helfgott-Schreier argument, they said if you have 2 random generators, then the diameter will be n squared log n squared times log n, or really this can be anything tending to infinity. But if you have 3 random generators, then you can give an analogous thing with this XWYZ trick, and you can reduce this to n squared times log n. So you can reduce this power to 1. And this is interesting because that's probably the best you can do for any argument that looks like this, for any argument that says, okay, let's first find an element of minimal degree, and then once we have an element of minimal degree, then we'll get everything else. Because you don't expect to get an element of minimal degree before n log n steps, and then there's another n steps to go.
And the minimum is n squared. It can be, right? That's what you said. You can get below n squared.
Yeah, so the absolute minimum would be n log n. So that's log the size of the group.
Right. No, but here it is for random generator, right? Okay. Because for worst case you need n squared, but for random it could be n log. It should be n log n, probably, right?
That's right. Yeah. Well, yeah. Depending on your beliefs.
Okay. I'm atheist, but
Okay. Are there any more questions? So let's take some again. Thank you very much for coming all the way.
Thank you for listening.
Okay.